Imagine standing on the surface of the moon. No wind, no sound. Not even the faint hiss of a breeze you didn't realize you'd always taken for granted. Just a sky so black and absolute that it feels like the universe itself is pressing down on you with the full weight of eternity. The ground beneath your boots is a fine gray powder that hasn't been disturbed in 1 billion years. Every footstep you take leaves a print that will still be there in 10 million years, because nothing on this world wears anything away. No rain, no frost, no erosion, no life. It looks peaceful. It looks still. It looks like the most serene place you've ever seen. And that stillness is the most dangerous lie in the entire solar system. We grew up thinking of the moon as friendly. It's right there, hanging in our sky every single night, close enough that you can see its craters with a cheap pair of binoculars from your backyard. We've been there. We planted flags, drove a car across its surface, hit golf balls into its dust. 12 human beings walked on it and came home alive. So it feels conquered. It feels familiar. It feels safe. It is neither of those things. Because the astronauts who walked on the moon didn't stay long enough to learn what it actually does to you. The longest any Apollo crew spent on the lunar surface was 74 hours and 59 minutes, just over 3 days. Compare that to a 6-month rotation on the International Space Station, or the 14-month endurance missions NASA is now planning for deep space. 3 days on the moon barely scratches the surface of what this world is capable of doing to a human body and a human mind. And what we've discovered in the decades since Apollo, through robotic orbiters, landers, remote sensing, laboratory analysis of returned samples, and a much deeper understanding of space medicine, should make us think very carefully, far more carefully than we currently do, before we ever send anyone back. Not because going back is wrong, but because the moon, for all its apparent stillness, is one of the most relentlessly hostile environments in the known universe. And we have been dangerously comfortable pretending otherwise. The problem started before the astronauts even got back inside the spacecraft. Every single Apollo crew reported the same thing. The dust. It got everywhere. It coated their suits in a thin layer of gray that no amount of brushing could remove. It clogged their equipment, scratched their visors with microscopic abrasions that slowly degraded their vision, and jammed the latches on their sample containers. When they tried to brush it off their suits before re-entering the lunar module, it didn't fall away the way dust on Earth does. It clung. It stuck. It behaved less like powder and more like a fine-grained adhesive. When they brought it inside the cabin, it became airborne in the low gravity and stayed airborne, drifting through the interior like smoke that had no intention of ever settling. The astronauts were breathing it. They knew it, and there was nothing they could do about it. Harrison Schmitt, the geologist on Apollo 17 and the last scientist to walk on the moon, developed what he called lunar hay fever within hours of re-entering the lander. His eyes burned intensely. His sinuses swelled almost completely shut. He was sneezing uncontrollably. Other members of multiple crews reported sore throats that lasted for days, persistent nasal congestion, and watery, irritated eyes. And every single one of them described the same strange phenomenon, an unmistakable smell that greeted them every time they opened their helmets in the cabin. The smell of burnt gunpowder. That smell was the dust reacting with oxygen and moisture inside the cabin for the very first time in its existence. On the lunar surface, where there is no atmosphere and no water and no air of any kind, the soil exists in a state of chemical suspended animation. Billions of years, and we mean that literally billions, of micrometeorite bombardment have ground the ancient rock of the moon's crust into particles finer than talcum powder. But these are not the soft, rounded particles you'd find in a desert or on a beach. On Earth, particles weather. Wind and water tumble them against each other, rounding their edges, neutralizing their chemical surfaces. The moon has none of that. Each grain of lunar regolith is a tiny shard of broken glass, its edges sharp at the atomic level, its chemical surface pristine and reactive because it has never been exposed to anything but vacuum and radiation. When those particles finally encounter oxygen or moisture for the first time, inside a habitat, inside a spacecraft, inside a human lung, they become chemically reactive in ways we are still working to fully understand. They bond to surfaces. They bond to tissue. They don't let go. And, unlike ordinary dust, which your immune system and respiratory tract can usually handle and expel, lunar particles are terrifyingly small. Many are smaller than a single micron, 1/1,000,000th of a meter, which places them in the same size category as the most dangerous airborne particulates on Earth. In Earth's gravity, inhaled particles of this size still tend to settle, and the cilia lining your airways work to move them toward your throat where you can expel them. On the moon, with gravity only 1/6 of what we're used to, not the 1/6 figure you see in some older references, but exactly 1.62 meters per second squared, compared to Earth's 9.8. Those same particles hang suspended in the air of a habitat for dramatically longer periods. They travel deeper into the respiratory tract. They reach the alveoli, the tiny air sacs deep in the lungs where gas exchange happens, and down there are no cilia. There is no cleaning mechanism. What reaches the deep lung tends to stay in the deep lung. NASA took this seriously enough to establish a dedicated research body, the Lunar Atmosphere and Dust Environment Explorer Program, and, separately, the Lunar Dust Toxicity Assessment Group, specifically to study what lunar dust does to human biology. What they found was deeply complicated and, in some ways, deeply alarming. The dust contains silicate compounds chemically similar to the crystalline silica that causes silicosis in miners and quarry workers on Earth, a progressive, irreversible, and ultimately fatal lung disease, characterized by the formation of nodular lesions and fibrosis in the lung tissue. It also contains nanoscale iron particles embedded in the glassy shells of the soil grains, particles that are highly chemically reactive when exposed to biological tissue. And it contains traces of minerals and compounds that simply have no equivalent in any industrial or natural dust hazard database on Earth. We are dealing with something genuinely novel. Research using lunar soil simulants, synthetic materials designed to mimic the physical and chemical properties of real lunar regolith, has suggested that the dust acts as a significant physical irritant at minimum, and that at higher or prolonged exposures, the potential for chronic respiratory damage is real and probably serious. One study from the University of Technology, Sydney, did find that certain lunar simulants were less acutely toxic than urban air pollution in Sydney, which sounds reassuring until you look at what that comparison actually means. The Apollo astronauts had no air filtration systems worthy of the name, no properly sealed airlocks, and essentially no reliable way to keep the dust out of their lungs. They were exposed for 3 days. A future lunar base crew will be exposed for weeks, months, possibly years. The dust from the permanently shadowed craters near the lunar South Pole, regions where sunlight has literally never penetrated since the solar system formed, may behave differently from the dust the Apollo crews encountered at equatorial latitudes. The chemical properties of perpetually cold, radiation-bombarded regolith are not the same as surface regolith. Nobody knows yet. Nobody has tested it. We are planning to send people to live near these craters, and we do not yet know what the dust there will do to them. But the story of lunar dust is stranger and more dangerous than just what happens when you breathe it. The dust also does something that borders on science fiction. On the sunlit side of the moon, solar ultraviolet radiation is intense enough, far more intense than anything that reaches Earth's surface through our atmosphere, to knock electrons directly off the surface of the soil. This gives the sunlit ground a positive electrical charge. The tiniest dust grains, the ones measuring less than a micron across and weighing almost nothing, pick up enough of this electrostatic charge to be physically repelled from the surface. They are launched into the vacuum above the moon. They hover. They float. Some theoretical models suggest that these electrostatically levitated particles can reach altitudes of meters, possibly even kilometers above the surface, forming a thin but persistent envelope of levitating glass shards around the entire sunlit hemisphere of the moon. On the dark side, the process reverses. Electrons from the solar wind, the constant stream of charged particles flowing outward from the sun, accumulate on the lunar surface, giving it a negative charge that can launch particles even higher. At the terminator, the moving boundary between the sunlit and shadowed hemispheres, horizontal electric fields of significant strength develop, and these fields may drive dust sideways across the surface in patterns that researchers have described as a kind of lunar dust storm. Not a storm driven by wind, because there is no wind. A storm driven purely by electrical forces, invisible and silent and impossible to see coming. The moon isn't just covered in dangerous powder. The powder is alive with electrical energy, constantly lifting, drifting, and resettling in ways that no one fully predicted before we started studying this phenomenon seriously. The dust doesn't just sit on the ground waiting for a boot print to disturb it. It moves on its own. It will find your equipment. It will find your solar panels. It will find your spacesuit seals. And it will do so whether you walk through it or not. Now add radiation, and this is where things move from serious to potentially catastrophic. The moon has no magnetic field and no atmosphere. On Earth, we live inside a magnetic cocoon and beneath an atmospheric blanket that together form one of the most effective radiation shields in the solar system. Our magnetic field deflects the vast majority of charged particles streaming from the sun. Our atmosphere, all 10,000 kilograms of air stacked above every square meter of ground, absorbs and blocks enormous quantities of high-energy radiation. We don't think about any of this because we've never had to. The protection is invisible, constant, and extraordinarily effective. On the moon, you get the full dose of everything the sun and the galaxy can throw at you, every second of every day. The first threat is galactic cosmic rays, the nuclei of atoms that have been stripped of their electrons and accelerated to nearly the speed of light by the cataclysmic explosions of ancient supernovae and other extreme astrophysical events across the Milky Way. These particles arrive from all directions, at all times, carrying energies that dwarf anything produced by human particle accelerators. They pass through spacecraft walls as if they weren't there. They pass through human tissue as if it weren't there. As they go, they shred DNA strands in every cell they pass through, producing the kind of double-strand breaks that are the most difficult for cellular repair mechanisms to fix correctly, and the kind most likely to cause mutations that lead to cancer. The shielding problem posed by cosmic rays is one of the most frustrating and counterintuitive challenges in all of space engineering. Unlike visible light or even X-rays, cosmic rays cannot simply be blocked by adding more mass. When a galactic cosmic ray hits a thick metal wall, say, the aluminum hull of a spacecraft or a habitat, it doesn't stop. The impact shatters atoms in the wall itself, producing what is called a secondary radiation shower, a cascade of neutrons, gamma rays, and charged fragment particles that scatter in every direction inside the habitat. More shielding means more secondary particles. The astronauts inside a heavily shielded spacecraft can actually receive a higher radiation dose than they would in a lightly shielded one, because the thick walls are converting one high-energy primary particle into dozens of lower-energy secondary particles, all of which deposit their energy in human tissue. This is not a solvable problem with current materials. It is a fundamental physical reality that the engineering community has not yet found a way around. On top of this constant background of galactic cosmic rays, there are solar particle events. These are sudden, violent eruptions from the sun, solar flares, and the massive plasma ejections associated with coronal mass ejections that can flood the entire inner solar system with high-energy protons in a matter of hours. They are largely unpredictable. They can arrive with almost no warning. And on the moon, with no magnetic field and no atmosphere, a major solar particle event could deliver a potentially lethal radiation dose to an unshielded astronaut in less than a day. On the International Space Station, astronauts dealing with a solar particle event can shelter in more heavily shielded sections of the station and still benefit from partial protection provided by Earth's magnetic field, which extends far enough into space to partially shield the ISS orbit. On the moon, there is no such refuge. The only shelter would be a deeply buried habitat, ideally under several meters of lunar regolith, which provides reasonable shielding, or a rapid retreat to a pre-positioned storm shelter. Neither solution is trivial to implement, and neither eliminates the risk entirely. The Apollo missions were, in a very real sense, extraordinarily lucky on this front. The mission planners knew the danger and scheduled flights to avoid the peak of the solar activity cycle. But luck is not a safety system. The August 1972 solar particle event, one of the most powerful ever recorded, occurred in the gap between the Apollo 16 mission in April and the Apollo 17 mission in December. Had either mission been on a slightly different schedule, the crew on the lunar surface during that event would likely have received a radiation dose severe enough to cause acute radiation syndrome. Nausea, vomiting, fatigue, and immune system suppression beginning within hours, followed by the longer-term consequences that could have been fatal. The storm missed the astronauts by months, not by design, by luck. A permanent lunar base will not be able to rely on luck. Then there is the temperature. The moon's thermal environment is one of the most extreme anywhere in the solar system, not because the temperatures are the highest or the lowest, but because of the combination of magnitude and cycling that creates a uniquely destructive pattern for both equipment and human habitation. During the lunar day, which lasts approximately 14 Earth days, because the moon rotates so slowly that the sun takes 2 weeks to cross its sky, the surface bakes in direct sunlight to temperatures of around 127 degrees Celsius. That is hotter than the boiling point of water at sea level on Earth. The ground itself radiates heat upward. Equipment sitting on the surface absorbs this heat with no atmosphere to carry any of it away by convection. During the lunar night, another 14 Earth days of complete darkness, surface temperatures plunge to around negative 173 degrees Celsius. That is cold enough to make most metals brittle. It is cold enough to condense gases that are liquid at room temperature. It is cold that no Antarctic winter, no high-altitude observatory, no deep polar ocean can match. That is a temperature swing of 300 degrees Celsius, occurring on a regular 2-week cycle, with no buffer of any kind. No air to moderate the transition, no cloud cover, no ocean heat to absorb and redistribute thermal energy. Just raw solar heating and the absolute cold of the vacuum of space, trading places with mechanical regularity every 2 weeks for as long as the moon has existed. The engineering consequences of this thermal cycling are severe. Every material expands when heated and contracts when cooled. Every joint, every seal, every electronic component, every wire, every structural element in a lunar habitat or rover undergoes this full 300-degree expansion and contraction cycle twice per lunar month. Metal fatigue accumulates, seals crack, polymer materials that depend on flexibility to function become rigid and then brittle. Electronics that cycle through extreme heat and extreme cold eventually fail in ways that are difficult to predict and difficult to diagnose. The Apollo missions lasted a few days, not nearly long enough for thermal cycling to become a critical factor. The Artemis missions are planned to last weeks. A permanent lunar base would need to survive thousands of these cycles, year after year, decade after decade. Every joint, every wire, every seal would be tested to destruction by the relentless thermal hammering of a world with no air to soften the blow. And then there is the ground itself, and this is where the story of the moon gets genuinely unsettling in a way that most people never hear about. The moon is shrinking, slowly, steadily, and with consequences that reach directly to the surface where we plan to build. As the moon's interior gradually cools, a process that has been ongoing since the solar system formed 4.5 billion years ago, the entire body is contracting. Over the last few 100 million years, the moon's circumference has decreased by more than 45 meters. For a world more than 10,000 kilometers in diameter, this sounds trivial. In geological terms, it is not trivial at all, and the reason lies in the fundamental structure of the moon's interior. Unlike Earth, the moon has no tectonic plates. Earth's surface is divided into a dozen or so large plates and numerous smaller ones, all floating on the partially molten layer beneath, constantly moving, subducting, colliding, and rifting. This tectonic activity continuously relieves the mechanical stress that builds up as the planet changes shape and temperature over time. The moon has none of this. Its crust is a single, rigid, brittle shell encasing the entire globe. When the interior contracts and puts the crust under compressional stress, there is no plate boundary to absorb that stress. The crust doesn't bend, it doesn't flex, it breaks. Sections of crust are pushed up and over adjacent sections, creating steep cliff faces called lobate scarps, thrust fault escarpments that stretch for kilometers across the surface and rise tens of meters above the surrounding terrain. The Lunar Reconnaissance Orbiter has found thousands of these scarps distributed across the entire globe of the moon, including many that are geologically young enough to be essentially brand new by any meaningful astronomical standard. Which means the shrinking is not a relic of the past. It is happening now. The moon is cracking under its own contraction right now while you watch this video, and it will still be cracking when the first Artemis boots touch down on the South Pole. The cracking produces moonquakes, and not the relatively harmless, deep, infrequent tremors that the Apollo seismometers detected, and that scientists had largely written off as geologically minor events. There is a second category of moonquakes that is far more concerning: shallow quakes, originating close to the surface along active thrust fault lines, in exactly the regions where these lobate scarps are found. In 2024, a study led by Thomas Waters at the Smithsonian Institution and Nicholas Schmer at the University of Maryland analyzed the strongest shallow moonquakes in the Apollo seismic record and found direct links between those events and young thrust faults in a specific region, the lunar South Pole. The same region NASA has designated as the target for the Artemis 3 crewed landing. The same region considered most promising for finding water ice and establishing a long-term human presence. One of the primary candidate landing sites, Daguerreaulashe Rim 2, sits in disturbingly close proximity to identified young fault scarps where this compressional activity is ongoing. But it's not just the presence of faults that should concern mission planners. It's what a moonquake actually does to the lunar environment that makes it uniquely dangerous. On Earth, seismic waves travel through a planet that is geologically active, wet in its upper layers, and covered with a thick regolith full of moisture and biological material that absorbs and dissipates seismic energy quickly. An earthquake, however severe, typically lasts seconds to a minute or two. The energy disperses, the ground stops shaking, and the structural damage is done. On the moon, the crust is dry, fractured, rigid, and completely airless. Seismic energy propagates through this medium with almost no dissipation. A shallow moonquake near an active fault does not ring for seconds. It rings for hours, like striking a perfectly dry bell with a hammer. the ground shakes and shakes and shakes, continuing far beyond any point at which an earthquake of equivalent magnitude would have stopped. And in a world where the near-surface layer is loose, unconsolidated rubble, billions of years of impact ejecta, fragmented rock, and the very regolith we've been discussing, sustained vibration of this kind can trigger slope failures and landslides on the steep inner walls of craters, particularly the permanently shadowed craters at the South Pole, where water ice is thought to be concentrated. The very craters we are most interested in. The very craters whose floors have never been disturbed since they formed billions of years ago. The 2025 follow-up study by the same research team went further. They analyzed the Apollo 17 landing site in the Taurus-Littrow Valley, the most carefully studied piece of lunar real estate in history, and found compelling evidence that boulder falls and landslides in that valley were not caused by meteorite impacts, as had previously been assumed, but by moonquakes. Specifically by repeated shallow moonquakes along the Lee-Lincoln Fault Scarp, which runs directly through the valley. This fault has produced magnitude 3 events repeatedly over the last 90 million years and may still be seismically active today. The statistical risk estimate the researchers derived was sobering in the way that very small probability numbers can sometimes be. They calculated roughly a 1 in 20 million chance of a damaging moonquake occurring on any given day near an active fault zone. Take a moment to sit with that number. It sounds extraordinarily safe, and for a single day, it is. But humans are not visiting the moon for a single day. They are going to live there. Over a decade of continuous habitation near an active fault zone, that daily probability compounds into a cumulative risk of roughly 1 in 5,500. For context, that is considerably better odds than being dealt 4 of a kind in a standard poker hand. Not a certainty, not even close to a certainty, but a real, quantifiable, non-negligible risk of a prolonged and potentially structurally damaging seismic event at a site where the habitat provides no earthquake-grade structural protection, where there is nowhere to evacuate to, and where help is a minimum of 3 days away under ideal circumstances, and weeks away under realistic ones. And as of early 2026, researchers at the Smithsonian have now cataloged over 2,600 individual lobate scarps distributed across the lunar surface, small ridges, all formed by the same compressional forces, all pointing to the same conclusion. The shrinking is global. The faulting is everywhere. There is no region of the moon that is categorically safe from this process. And through all of this, there are the micrometeorites. On Earth, the atmosphere is the planet's first and most comprehensive defense against the constant rain of small space debris that fills the inner solar system. Objects the size of a grain of sand enter the atmosphere at speeds of up to 70 kilometers per second and burn up in the upper atmosphere, producing the brief streaks of light we call shooting stars. Objects the size of a pea rarely reach the ground. Even objects the size of a fist usually fragment and burn before impact. The atmosphere is remarkably good at this. It has been protecting everything on the surface for billions of years, and we have grown so accustomed to that protection that we don't think about it at all. On the moon, there is nothing to stop them. Particles the size of sand grains strike the surface at speeds of up to 10 kilometers per second, roughly 36,000 kilometers per hour, with no deceleration, no heating from atmospheric entry, no warning of any kind. They have been doing this for over 4 billion years, which is precisely what has ground the surface into the razor-sharp powder we have been discussing. The entire history of the lunar surface is a record of this relentless kinetic bombardment. For a habitat or a spacesuit, the risk from any single micrometeorite is small. Most particles are tiny, and the energy they carry, while significant, is not enough to breach a properly constructed structure. But over months and years, the cumulative effect is very real and very damaging. The Apollo astronauts discovered that the lunar dust, driven in part by these constant micrometeorite impacts, had eaten through multiple layers of the outer boot material on their spacesuits in just a few days of surface operations. The vacuum seals on sample containers were destroyed by microabrasion. The optical coatings on visors were measurably degraded. And the Apollo crews were on the surface for 3 days. A permanent structure on the surface would face this sandblasting effect continuously, 24 hours a day, 365 days a year, decade after decade. Every external surface, every solar panel, every camera lens, every antenna, every meter of pipeline or cable running across the surface would be subjected to constant micro-scale impacts. There is no maintenance crew available to do routine inspections. There is no hardware store for replacement parts. Every component that fails is a crisis, because the backup has also been exposed to the same environment for the same duration, and every failure cascades into the next. This is the cascade problem, and it is perhaps the most insidious danger of all. In a terrestrial engineering environment, systems fail one at a time, and you fix them. On the moon, everything degrades simultaneously. The thermal cycling weakens structural seals. The micrometeorite bombardment abrades external surfaces. The radiation degrades electronics. The dust infiltrates mechanisms. The moonquakes stress foundations. None of these processes respect boundaries between systems. A dust-jammed valve in a life support system and a thermally cracked seal in a water recycling system are not independent events. They are co-occurring degradations of a tightly coupled system that must function at essentially 100% reliability because human lives depend on it continuously, with no possibility of rapid rescue or resupply. Compare this to the analogy that NASA engineers themselves sometimes use, the International Space Station. The ISS has been continuously inhabited for over 24 years, and it has required an enormous and unbroken chain of resupply missions, repair spacewalks, component replacements, and software updates to maintain habitability. It has a crew of trained engineers who can diagnose and fix problems in real time. It has an escape vehicle, a Soyuz or Dragon capsule, docked and ready at all times, capable of returning a crew to Earth in a matter of hours if the station becomes uninhabitable. And crucially, it orbits Earth at an altitude of just 400 kilometers, bathed in the partial protection of Earth's magnetic field, with resupply missions measured in days. A lunar base has none of these advantages. Resupply missions take days to weeks minimum. Emergency evacuation requires landing a vehicle, which requires a functioning launch pad and a launch-ready spacecraft. Radiation exposure on the lunar surface is dramatically higher than on the ISS, and the engineering environment is incomparably more hostile on every metric we've discussed. Now consider what all of this does to the human body over time. Not over 3 days, over months. The gravity question is one that sounds simple, but is actually deeply complicated. 1/6 of Earth's gravity, 0.165 g to be precise, is not zero gravity. It is not the microgravity of the ISS. It exists somewhere in between, in a regime that we have almost no long-term human physiological data for. We know in great detail what zero gravity does to the human body over 6 months on the ISS. Significant bone density loss, muscle atrophy, cardiovascular deconditioning, fluid shifts that cause visual changes and increased intracranial pressure, immune system alterations, and psychological stress. We have reasonable protocols for managing and partially counteracting these effects in microgravity, though they are far from perfect. What 1/6 gravity does to the human body over 6 months or a year is genuinely unknown. It might be enough to substantially reduce the bone and muscle loss seen in microgravity. It might not be. The threshold of gravity needed to maintain long-term skeletal health in humans is not known. We have never had a subject to test it on. The first people to live on the moon for extended periods will be conducting this experiment on themselves, in real time, with no baseline of knowledge to draw from. 38% of Earth's gravity, which is roughly what Mars offers, is similarly uncharted territory, and yet Mars is considered by some as the more serious long-term target. The difference is distance and the psychology of rescue. Mars is, at minimum, a 6-month journey away. The Moon is 3 days, but the Moon's gravity, lower even than Mars, may present physiological challenges that its advocates consistently underplay. And then there is the mind. The psychological literature on isolated, confined environments is rich and largely disturbing. Antarctic overwintering stations, nuclear submarines on extended patrols, the Biosphere 2 experiment, simulated Mars missions in analog facilities. All of them have documented a characteristic progression: initial enthusiasm and high motivation, followed by the onset of monotony, interpersonal friction, cognitive decline, sleep disruption, and what researchers call the third quarter phenomenon, in which morale and performance drop most severely in the period between the halfway point and the final quarter of a mission. These effects emerge in environments where participants can go outside, where they can look at a natural sky, where they can, at minimum, make a phone call home and hear an answer within seconds. On the Moon, communication with Earth involves a one-way signal travel time of approximately 1.3 seconds, which rounds to a minimum 2.6-second round trip for any exchange. That sounds like almost nothing. In practice, for real-time conversation, it introduces a noticeable and surprisingly disorienting delay. For emergency communication with mission control, not the smooth, scripted exchanges of a nominal mission, but the panicked, rapid-fire communication of a system failure in progress, that delay is significant. For teleoperated robotic systems where a human operator on the Moon is trying to remotely control something in real time, 2.6 seconds of round-trip latency is the difference between precision and chaos. And the visual environment of the Moon is itself a psychological challenge that is rarely discussed. The sky is black, always black. Even in full daylight, the sky above you is completely black because there is no atmosphere to scatter sunlight. The sun hangs in that black sky like a hard, merciless disk, smaller than it looks from Earth, but more intense, unfiltered by any haze or atmosphere. The shadows on the lunar surface are absolutely black, with no scattering to soften them. The contrast between the intensely lit ground and the absolute shadows of crater walls is beyond anything the human visual system is designed to handle. Apollo astronauts described the experience of walking near shadowed areas as deeply disorienting, as if parts of the landscape had simply been cut out of reality and replaced with darkness. There is no color. The surface is gray. The sky is black. The sun is white. For weeks, then months, then years, this would be the visual world of a lunar resident. The psychological effect of this monochromatic, high-contrast, completely alien environment on long-duration crews is an open research question. Analog environments on Earth, underwater research stations, polar bases, nuclear submarines, provide some insight, but nothing truly comparable to the visual and sensory experience of another world. Now, some will argue, and it is a reasonable argument, that robots don't have any of these problems. And they are correct. Robots don't breathe. Robots don't develop hay fever from glass powder. Robots don't need gravity to maintain their skeletal integrity. Robots don't experience the third quarter psychological phenomenon. Robots are, on every metric we've discussed, better suited to the hostile environment of the Moon than human beings are. The counterargument is also real. Robots are extraordinarily capable in structured environments performing defined tasks. They are brittle in novel situations. The Mars rovers, Opportunity, Curiosity, Perseverance, have produced extraordinary science and have justified every dollar spent on them. But they have also spent months waiting for software updates, lost power during dust storms, gotten stuck in sand, driven into rocks, and in the case of Opportunity, simply stopped responding after 15 years. None of this was catastrophic because no human lives depended on their continued function. Opportunity's silence was a loss for science. It was not a tragedy. The argument for human presence on the moon is essentially an argument about cognitive flexibility. A trained geologist standing on the rim of a crater can, in a few minutes of direct observation and physical interaction with the environment, gather information and make decisions that would take a robotic rover years to replicate. Human beings are, for now, still significantly better than robots at improvisation, at recognizing the unexpected, and at adapting to situations that were not anticipated in mission planning. The question is whether the gains from human cognitive flexibility outweigh the enormous costs and risks of keeping humans alive in this environment. That calculation changes as robots become more capable, and robots are becoming more capable very quickly. There is also the question of what the moon is not. It is not, despite the way it is sometimes discussed in the popular science space, a backup for humanity. This framing appears regularly in conversations about space exploration and the long-term survival of the species. If Earth becomes uninhabitable for any reason, we can move to the moon or to Mars, and humanity will survive. It sounds compelling. It is, if examined carefully, a significant distortion of what these environments actually are. The moon, as we have established, is covered in glass powder that attacks the lungs. It is bathed in radiation that has no adequate shielding solution. It shakes from internal contraction that will persist for geological timescales. It cycles through temperatures that destroy equipment. It has no liquid water on its surface, no breathable atmosphere, no magnetic field, no soil capable of supporting agriculture without extraordinary technological intervention. Every calorie consumed by a lunar resident requires either shipment from Earth or production in a closed life support system of extraordinary complexity. Every molecule of oxygen requires generation. Every liter of water requires recycling with near-perfect efficiency. Keeping 8 billion humans alive on the moon is not a backup plan. It is a technological undertaking that makes the construction of the International Space Station look like assembling flat-pack furniture. The moon is not a lifeboat. It is not a garden waiting to be planted. It is one of the most efficiently hostile environments the solar system has to offer, and the idea that it represents a solution to existential risks on Earth fundamentally misunderstands both the scale of the challenge and the nature of the risks. Terraforming is even further from reality than it is usually presented. Mars, at least, has a day length close to Earth's, an axial tilt that creates seasons, evidence of ancient water, a thin atmosphere that could theoretically be thickened over geological timescales with sufficient technology. The moon has none of these advantages. Its day is 29.5 Earth days. It has essentially no atmosphere and no mechanism to hold one. The low gravity and lack of magnetic field mean that any atmosphere we tried to create would be stripped away by the solar wind over millions of years. The moon is not a candidate for terraforming in any time frame that is meaningful for human civilization. It is not Earth 2. It is not even a rough draft of Earth 2. What the moon is, genuinely, scientifically, stripped of the romance and the nostalgia of Apollo, is a scientifically valuable, strategically important, and profoundly dangerous place that human beings can visit, carefully and briefly, and with extraordinary technological support, and from which we can learn things about the history of the solar system and about the physiological limits of human adaptation that we cannot learn any other way. It is worth going to. It may be worth establishing a permanent presence there. But it demands a level of engineering rigor, medical understanding, and operational humility that our current public conversation about returning to the moon does not consistently reflect. This is what the moon actually is, not the gentle silver companion that hangs in our sky and makes the ocean tides. Not the conquered stepping stone that we visited and left behind, flags still standing in the airless calm. not the first easy rung of a ladder to the stars. It is a world wrapped in glass powder that clings to everything, floats on its own electrical charge, and attacks the lungs of anything that breathes it. A world where radiation pours through your bones every second you stand on the surface, and there is no wall thick enough to stop the worst of it. A world that is quietly tearing itself apart from the inside, sending new cracks across its own face and shaking the ground for hours at a time in the very regions we have chosen to build. A world where the temperature swings from boiling to freezing every 2 weeks, where equipment is destroyed by the cycling before it can be repaired, and where invisible grains of glass travel at bullet speeds through the vacuum above your head. We went there 6 times. Each time we stayed for less than 3 days. We were visitors passing through too quickly for any of these dangers to fully reveal themselves. We took our photographs, collected our rocks, planted our flags, and came home to a planet that was trying very hard to keep us alive. Going back is one thing. It is noble and scientifically motivated and probably necessary. Staying is something else entirely. And the moon, as always, will be waiting. Quiet, patient, beautiful in its barren way, and far, far more hostile than it looks. I hope you enjoyed the video. If you did, please consider leaving a like. It genuinely helps more people find this content. And if you want to keep exploring the universe and the surprising, counterintuitive, sometimes unsettling truths it contains, subscribe and hit the notification bell so you never miss a new video. Thanks for watching, and I'll see you in the next one.